بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. طلاب المعهد العالي لهندسة التكنولوجيا بكفر الشيخ، الفرقة الثانية، لائحة قديمة. أهلا بيكم في محاضرات مادة المايكرو بروسيسور للعام الجامعي 2020-2021 الفصل الدراسي الأول. زي ما انتم شايفين الكود بتاع المادة EEC 2103. معاكم دكتور أسامة ثروت. إن شاء الله هنكون مع بعض في المادة دي، والمادة دي إن شاء الله هتكون تتمحور حوالين دراسة المايكرو بروسيسور، وهناخد assembly language لل 8086، وقبلها هناخد برمجة لأحد الأجهزة القديمة الجيل الأول اللي هو IAS. المحاضرة بتاعت النهاردة هتكون ملخص عن تاريخ الكمبيوتر. تمام، دي رؤية المعهد. طبعا احنا بنحب دائما في كل مناسبة ان احنا نذكر برؤية المعهد ورسالته. ورؤية المعهد بتاعنا اللي هو المعهد العالي لهندسة التكنولوجيا كفر الشيخ أن يكون المعهد رائدًا ومعتمدًا أكاديميًا في مجال العلوم الهندسية والتكنولوجية على المستوى المحلي والإقليمي والدولي. طبعًا الرؤية معناها إيه؟ معناها المعهد بيحلم بإيه؟ عاوز يوصل لإيه؟ طيب رسالة المعهد: يلتزم المعهد العالي لهندسة التكنولوجيا بكفر الشيخ، وزارة التعليم العالي والبحث العلمي، بإعداد خريجين متخصصين في مجالات الهندسة والتكنولوجيا طبقًا للمعايير القومية الأكاديمية المرجعية، ملبين احتياجات سوق العمل المحلي والإقليمي، وقادرين على إجراء بحوث علمية مبتكرة وتقديم خدمات مجتمعية وتدريب ميداني واستشارات هندسية في إطار القيم الأخلاقية. أول جزء لينا في الكورس بتاعنا الهيستوري اوف. طبعا مهم خالص ان انت تبقى عارف ان كلمة كمبيوتر جاية من فيرب كمبيوت يعني يحسب. فيبقى كلمة كمبيوتر هو الحاسب مثلا، أو الشيء اللي بيحسب. فطبعا زي ما هو معروف إن أول حاسب هو الإنسان، كان بيعد على صوابعه، بيعد على الحصى، بيعد على أي شيء. فده الكمبيوترز، أول كمبيوترز هو البيبل. هو هنا قال لك إن the first computers were إيه people. تمام. طيب أنت هتلاحظ الآتي لما تيجي تبص لتاريخ الكمبيوتر ونشأة الكمبيوتر، هتلاقي هو نشأته دائما وأبدا كانت مبنية على الحاجة، زي ما بيقولوا كده الحاجة أم الاختراع. فكان الإنسان في الأول خالص بيستخدم الحصى، بيستخدم صوابعه إن هو يعد وهكذا. فبدأ مثلا إن هو بدأوا في عملية جمع الضرايب، في عملية عد أشياء، في عملية حساب حاجة. فبقى الأمر فيه صعوبة، خصوصا لما الأمر ده يتطلب دقة وتكون الأخطاء أقل ما يمكن. فبدأ الإنسان يفكر في آلة تساعده في الموضوع معايا. فدي كانت أهم شيء كحاجة ل أو أهم سبب لنشأة الكمبيوتر. ممكن الحاجة دي تتنوع بين ممكن تكون حاجة عسكرية، الدولة عاوزة تتفوق على دولة، أو ممكن تكون حاجة اقتصادية، دولة عاوزة تتقدم وهكذا. تمام. طيب أول نقول جهاز أو آلة استخدمها الإنسان في عملية العد كانت الآلة اللي اسمها أباكوس. اللي انتوا شايفينها دي اللي هي عبارة عن الخرز دوت. كان بيستخدم الخرز ده في إن هو يبدأ يعد معايا. طيب زي ما انت شايف إن الآلة دي عبارة عن خرز. لو بصيت هنا هتلاقي 5 وهنا 2، 5 2 وهكذا. فمثلا لو هو عاوز يعد زيرو هتلاقي كل الخرز ده تحت. طب عاوز يعد واحد، يجيب الخرزة دي ويروح رافعها لفوق يبقى واحد. طب 2، الخرزة دي تبقى 2، طلع دي يبقى 3، يبقى ال3 دول في فوق ال3 معايا هيبقى عدي 3. طب 4 يطلع دي، طب 5 يطلع دي، طب 6 معايا يطلع ديت وهكذا. هنشوف دلوقتي فيديو سريع عن استخدام الايه الاباكس.
Okay, right now, what you see at the abacus in its cleared state says 0. There are no numbers on the board, and even though 0 means nothing, or you don't really consider it a number. 0 is a number. And when no beads are touching the center beam or the reckoning bar, that number indicates 0. So the first number we're always going to use is the number 0. And each beam has 10 numbers, including 0. One more thing before we start counting is that for now, I want you to not worry about these 3 beams right here. Just let them be. They can ignore them. After this dot that you see right here, we're going to have this beam right here be our ones column. And I'll explain that a little bit later. But this is where we're going to start counting, is the first brown column here, or the third one from the right. Okay, so here we go. Let's start counting. Right here, the first number that we have is 0. Congratulations, you counted to 0 on the abacus. Feels good, doesn't it? Now let's do 1. Let's see if we can do this. Take a deep breath. 1. How does that feel? You just counted to 1 using the abacus. Now, as you might imagine, 2 is probably a piece of cake. 2. There are 2 beads pushed up towards the center reckoning bar, and now we've counted to 2 using the abacus. You've probably already zipped past me and have already gotten to 4. There's 4 on the abacus, but what do we do next? Now remember, the top beads are worth 5 and the bottom beads are worth 1. So to do 5, I do that. That is the number 5 on the abacus. And you may have guessed this already because we talked about it a little bit before. That's 6, 7, 8, and 9. There we go. There is 0 to 9 on the abacus. Let's do it again. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's do, after 9 comes 10. Not a difficult transition, but it's important to recognize what's going to happen here because we're moving over one more place value. And to make the number 10, if you write the number 10, how do you write it? You do a 1 and a 0. So that's how we do it on the abacus. We move this column back to the 0 placement and put a 1 there. That represents the number 10. Now, 11 is a 1 and a 1. There is 11. 12, 13, 14, 15, 16, 17, 18, 19. Now what comes after 19? 20. And there you go. If you can get that, 30 is going to be a piece of cake. So let's do 21. 21 is written a 2 and a 1. So the same way you write a 2 and a 1 is how you do it on the abacus. We already got the 2 here. So 21, 22, 23, 24, 25, 26, 27, 28, 29. Now, before I do it, take a guess. Do it on your abacus. I hope you're doing this with me. What's 30? 30. And you can keep going through. But each time, 31, 32, 33, 34, 35, 6, 7, 8, 9, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. Uh-oh. What are we going to do for 50? Everything goes back. There's 50. Simple as that. a 5 here, and a 0 here. 5, 0 is 50. Now let's say we keep doing this. How would you do 100? 100. 155. 156. Okay? Now we're going to do a simple, very simple addition. We are going to do the addition problem of 1 plus 3. So here's the number 1, and we're going to add 3 to it. Wow, there it is. We now have the number 4. Let's do 2 plus 1. 2 plus 1 is 3. Okay, let's do a tough one. How about 0 plus 2? Well, right now it's reading 0, and if I do plus 2, there it is. 0 plus 2 is 2. Let's say we have the number 11. 1 and a 1. Right there is the number 11. And we're going to do 11 plus 2. Well, 2 is in the ones column. 11 plus 2 is a 1 and a 3. And we read that 13. So 11 plus 2, 11 plus 2 is 13. Okay, let's do another one. How about 12 plus 2? Well, here's the number 12, and if I add 2, I just simply slide up 2 beads on the ones column. 12 plus 2 is 14. A 1 and a 4 is the number 14. 41. Here we go. 41. That's a big number. 41 plus 3. That means I have to add 3 to the ones column. What number is that? A 4 and a 4 is the number 44. So 41 plus 3 is 44. Clear your abacus. 21. Let's add 21 and 22. So 22 is really easy to add to this. All I have to do is slide up 2 beads in both the tens column and the ones column. So 21 plus 22 is what? There's a 4 and a 3. 21 plus 22 is 43. Put the number 231 in your abacus, and we're going to add to that 111. So 231 looks like this. 231. There's the number 231 on your abacus. Now this is an easy one. I think you'll be able to do this. Now add 111. That's all ones. If you write the number 111, it's just 3 ones. And 1, 1 goes in each of these columns. So we go 1, 1, and 1. We just added 111 to that, and what are we left with? 342. So 231 plus 111 is, you just read it on your abacus, it's easy, 342. See how fast you can come up with that? It's pretty quick. One of the things, you love the abacus. All right, let's do another one. Even though it's 100, it's a piece of cake. So 123. 123, there's our number. And let's add to that 321. So 321, I move 3 beats here, 21. Oh, what did I end up with? 444. 440 and 4. 4 in the hundreds column, and so I say 400. 4 in the tens column, and I say that 40. And 4 in the ones column is 4. 444. Now subtraction isn't a bit harder, it's not even a little bit harder than addition. It's just the opposite. In math, everything has its opposites, and subtraction is the opposite of addition. See, that's easy. Piece of cake. Addition, subtraction. When I add, I move it towards the bar. When I subtract, I move it away from the bar. Add 1, take away 1. As easy as that. Add 2, take away 2. Add 3, take away 3. Add 30, take away 30. Add 1,324 and take away 1. That's how, easy as that. That's how we do it. So let's start with the ones. Here we go. Let's the first problem. 3 minus 1. 3 take away 1. However you want to say it. So if I'm going to take 3, if I have 3 and I want to take away 1 or subtract 1, then all I do is move that down. And what do I have left? 2. Piece of cake. Clear the abacus. Put 2 on there. This is, let's do 2 take away 2, or 2 minus 2. That means I move 2 beads away from the center beam. And what am I left with? 0. 4. 4 take away, or 4 subtract, 4 minus, however you want to say it. 4 minus 3 is, that means I have to take away 3 beads, move them away from the center bar, and the answer is 1. 4 minus 3 is 1. So we're going to start with the number 10 on our abacus. And we are going to subtract from that the number 7. Well, the 7 is in the ones column. We don't have enough beads there to take that away from it. So, remember, we've done it's exactly the same as we've done before. When we're using complements and we're subtracting, we're going to add the complement. All right, so here we go. We're doing subtraction. The complement to the number 7 is the number... Did you say it out loud? Can you get it? Did I? It's 3. The complement to the number 7 is 3. So here's what we do. Is we add 3, slide 3 towards the beam, and we're going to take that one away in the tens column. So 10 minus 7 is 3. I can see that. That works. Yeah, we can do this. Let's do another one kind of similar to that. Let's do 10 minus 6. And in your head, I know you can probably do this, but we're learning abacus brain. So here we go. 10 minus 6. This says 10, a 1 and a 0. And we don't have 6 beads to take away from here. There would have to be a number bigger than 6 in this ones column to do that. But there's a 0. So what do? We add the complement. The complement to the number 6 is 4. All right, that means we slide 4 up and take away this bead in the tens column. So 10 minus 6 is 4. All right, I can see the wheels starting to turn. Here we go. Let's do one just a tad bit. No, it's not any harder. It's just different. Let's do 11 minus 8. 11 is a 1 and a 1. That's how you write the number 11, 1 and 1. And we're going to subtract from that the number 8. 11 minus 8. So here we are in the ones column, and we don't have enough beads there. We only have 1. So we've got to use complementary numbers, and the complement to the number 8 is 2. That means we add 2. So I added 2 to the ones column, and I'm going to subtract this bead in the tens column. So 11 minus 8 is 3. All right, here we go. The next one, 12 minus 9. There is the number 12. 12 on our abacus, and we're going to subtract from that the number 9. Not enough beads. That means we add the complement. The complement to the number 9 is 1, and we take away that right there. 12 minus 9 is, what do we have left? 3.
زي ما انتوا شفتوا في الفيديو ان الاباكوس قدرنا ان احنا نستخدمها او هم استخدموها في عملية الجمع والطرح، والامر طبعا يعني اظن ان هو فيه سهولة وفي نفس الوقت فيه صعوبة زي ما انتوا شفتوا في عملية الطرح. وطبعا اللي معروض قدامكم في السلايد دي هو نوع من انواع الاباكوس زي ما انت شايف هنا في الخمسة بيز وهنا 2، لكن اللي كان موجود في الفيديو كان هنا في 4 و بخلاف الخمسة دي معايا. ده الشرح بتاع الاباكوس، طبعا الفيديو كان موضحه خالص تمام، وطبعا محتاج منك تدريب. زي ما انت شفته في اباكوس كان الجهاز ده او الآلة اللي عملوها دي كانت للجمع والطرح زي ما انت شفته، فكانوا محتاجين برضو الانسان طبعا محتاج ان هو يضرب، لان عملية الضرب ذات نفسها متعبة وفي نفس الوقت الخطأ فيها وارد بكتير يعني. فسنة 1617 جون نيبير اخترع آلة لتسهيل عملية الضرب، بدل ما انت تعملها بايدك انت، لا تستخدم الآلة دي في ان انت تقدر تجمع اي او تضرب اي ارقام في اي ارقام انت عاوزها. تعال هنشوف الموضوع ده. زي ما انت شايف ده هو بيسموها النيبيرز بونز او عظام نيبير، او يعني يقصد بها الستيكس دي. زي ما انت شايف هتلاقي الارقام من 1 لغاية 9، وهنا هتلاقي الستيكس دي او البونز دي مترقمة 1 2 3 4 5 6 لغاية 0 زي ما انت شايف. لو لاحظت هتلاقي ان الواحد ضرب واحد يطلع 1 0 اللي هي 1، يعني ده اكنه صف الواحد، يعني 1 في 2 2 0، يعني 2 3 4 وهكذا. تعال نشوف الستة اهو، 6 في 1 ب6، 6 في 2 ب12، 2 1 وهكذا. تعالى 9 18 آسف 9 18 27 وهكذا، والصفر كله صفار زي ما انت شايف. طب هو ازاي بيستخدمها بقى في عملية ان هو مثلا يضرب 3 ارقام في 3 ارقام؟ الامر في منتهى البساطة. هو تقدر تقول ان هو استخدم الآلة دي في ان هو بدل ما يضرب هيجمع، يعني هيحول عملية الضرب الى عملية جمع. هنشوف الكلام ده ازاي. دي شكل تاني للنيبير بونز معايا. فتعالى على سبيل المثال هو عاوز يضرب مثلا 8 في 7، هيجيب الستيك بتاعت ال8 وقدام السطر بتاع ال7 وهيلاقي 56. سهلة دي مفيش مشكلة. يبقى هو ضرب ايه؟ 1 ديجيت في 1 ديجيت اللي هي ايه؟ خانة واحدة في خانة واحدة. طب لو هو عاوز يضرب خانتين في خانة، فهيجيب الستيك بتاع ال8 او البون بتاع ال8 والبون بتاع ال6 اهو، وعند سطر ال7 يشوف هتلاقي عندك هنا 6 في 7 ب 42 و7 في 8 ب 56. اوكي، هيعمل هو ايه؟ طبعا خلي بالك دي الحركه اللي انت بتعملها بايدك، يعني ديت عمليه الايه؟ عمليه الضرب الطبيعيه بتاعتنا، لكن احنا مش هنعمل الكلام ده. احنا من هنا اهو هنطلع الناتج ده ازاي؟ هتلاقي الامر في منتهى البساطه. هياخد الارقام اللي هي موجوده على القطر ويجمعها. طيب الاثنين قصاد اي حاجه على قطر مفيش، يبقى ده 2، يكتب 2. طيب هنا 4 قصادها ايه؟ 6، يبقى عندنا هنا في الاول 2 و4 و6 10، يبقى صفر معانا الواحد، والواحد ينضاف على الخمسه يبقى 6. هتلاقي 6 0 2 تمام؟ تمام. تعالى لو هو عاوز يضرب 3 ديجيتس في 1 ديجيت، 3 خانات في خانه واحده، نفس اللعبه اهو. خد الاثنين، الستيك بتاع الاثنين، الستيك بتاع السته، الستيك بتاعت الايه الثمانيه. 7 في 8 7 في 2 ب 14، 7 في 6 ب 42، و7 في 8 ب 56. يبقى 4 اجمع 1 و2 3، و4 و6 10 يصفر معانا الواحد، وهنا 5 اتحط عليها الواحد يبقى يبقى أنت عندك 6 0 3 4 اللي هو ده. فإيه اللي حصل؟ أنت مش هتضرب ولا تعمل أي حاجة، أنت كل ما هنالك إن أنت إيه، أو يعني هم حول الضرب إلى عملية جمع زي ما أنتم شايفين. تمام. هنا يبقى تمام. طيب هنا برضو مثال تاني، ضرب هو 3 خانات في أدي 1 2 3 4 5 6. يبقى 3 خانات في 6 في 6 خانات. طبعا الموضوع هنا لو أنت عملته كعملية ضرب هياخد منك وقت طويل، لكن هو قدر باستخدام النيبير بونز ان هو يحول عمليه الضرب الى عمليه جمع. هناخد فيديو بس او نشوف فيديو بسيط للموضوع ده.
I'm going to multiply 6,473 by 8. Now we'll take the bones out. We need a 6 and then a 4, a 7 and a 3. So we need a 4, a 7 and a 3. And all we need to do now is take our answer grid and we're multiplying by 8. So we put it on at 8. And then we move down the diagonals and we get our answer. So there's only 1 in the first bit there. So you get 4 there, 2 plus 6 gives you 8, 5 plus 2 gives you 7, 8 and 3 gives you 11, so that's 1, carry 1 and we get 5, so we get 51,784. Now I'd like to show you it a bit bigger so you can see exactly where it's coming. I've used different colours so it's easier to see. The 4 there gives you 4. Down the next diagonal, 2 and 6 is 8, 5 and 2 is 7, 3 and 8 is 11, 1, and we carry the 10, so 1 plus 4 is 5, and our final answer, 51,784. Really easy, isn't it? The next thing we'll do is try some examples with bigger numbers. Now I'm going to show you how to multiply by a 2-digit number. I'm going to multiply 845 by 47. For this we're going to need to draw a 3 by 2 grid. Now to get the bones, we'll need to get an 8, a 4 and a 5. We're going to multiply by 40 first, so we've got to look at 4, so we set the grid on at 4, and there's our numbers there. I'm going to do them in different colours to make it easier to read the next bit. Nothing 1, you don't need to do them in different colours. 2, 6, 3, and you can see 321620 is what you'd do, 321620, and we now need the units, which is 7, so go down to the 7 and we do the same again, so you can see that would be 5, 2, 6, and that one's 5, that's 8 and 3, so it's just 5, 6, 2, 8, 3, 5, 5, 6, 2, 8, 3, 5, and that's all you do. You don't need to bother with the colours. You'll see just now why I put them in colour. All you do now is add down the diagonals. It's the same as what you did with just one bone, but now you've got 2 bones. So there, down that diagonal gives you 5, that diagonal gives you 8 and 3 is 11, we get 1 and 6 is 7, 9, 15, 17, carry the 1, you get 6, 7, 8, 9, and you've got a 3 there. So our answer is 39,715. That's how easy it is. And finally, in the last one we're going to multiply a really big one. We're going to do a 4-digit number by a 3-digit number. For the final example, I'm going to do 7,384 times 638. Now we're on to the really difficult sort of stuff. Normally, there's a traditional method of doing it with all the carries, extra zeros, all the complications. Quite hard going. As you've guessed, we're not going to do it by that method. We're going to do it really easily using Napier's bones. We're going to need a slightly bigger grid this time, so I've prepared it earlier to speed things up a bit. And we're all set to get going with the bones. The first bone we require is 7. So we pick a 7, pick a 3, pick an 8, and the final bone is 4, and that's a bone selected. Now, for the top line there, we're going to need a 6 for the 600, so we go down to the 6, and again, like I did the last time, to make it easier, I'm going to put it in 2 different colours. We'll make that 4, that one there's 4 and 8, and that one there's 4. Put the red in for the other ones. Again, you don't do this. This is just so I can show you the addition easily. And that's that line, 4218, 4824, 4218, 4824. Next line we need is the 30s, so we need to put it to 3 and read that off there. And you can see that's a 1, 4, that's got nothing there, and that's a 1. And I'm putting in the other ones in red, as I say, this is just to make it easier for the next stage. So we've got a 2 there, a 9 and a 2. And the final one is here 8, which is the units. So we go down to the 8, and again there we've got 3, 4, 2, 6, and I'll mark the other ones in blue, and we've got a 6, 4 and a 5, and there it is, 5, 6, 2, 4, 6, 4, 3, 2, oh missed 2, and you can see it's the same there. Now all we need to do is add, as usual, add down the diagonals, and we've got first diagonal 2, 4 plus 3 is 7, plus 2 is 9, 4 plus 6 is 10, plus 4, 14, 15, 19. Put 1 onto the 6 and we've got 7, 9, 18, 20, 28, 30. So we've got a 0, carry the 3, 3 and 5 is 8, 9, 17, 21, carry the 2, 2, 4, 6, 7, and we've got 4 up the top. So our answer has 4710992. So we have 4,710,992. Now, did you see how easy all of this was? The thing you should do now is to print out some bones to make up, or use the simpler strips, but you should really have a go at this. You'll really enjoy it. Napier's bones makes multiplication so easy.
بعد كده نيبير سنة 1632 استخدم يعني قدراته في موضوع اللوغاريتمات، في إن هو يعمل يعني آلة أو مسطرة فعلا بديعة، ويقدر يستخدم المسطرة دي في عملية الضرب والقسمة، وكمان في عملية التربيع وإيجاد الجذر التربيعي. الجميل في الموضوع ده إن المسطرة دي بيسموها السلايد رول، نيبير عملها في 1632 واستخدمتها ناسا لغاية الستينات. طيب المسطرة دي بتشتغل إزاي؟ تعال نشوف. المسطرة عبارة عن 3 أجزاء، مسطرة فوق، مسطرة تحت، وكيرسور. يبقى مسطرة فوق، مسطرة تحت، وفي عندي الكيرسور ده. طيب المسطرة اللي فوق دي بقدر أحركها يمين وشمال. تمام. والكيرسور ده عبارة عن قطعة إزاز كده وعليها علامة اللي أنتوا شايفينها وأقدر أحركها. تمام. طب إيه الفكرة؟ الفكرة كان إيه؟ دلوقتي تخيل إن أنت عاوز تضرب 2 في 3 بتساوي 6. لو أنت خدت لوج الطرفين هتلاقي إن ده هيبقى لوج، طبعا أساس 10، لوج 2 في 3 بالتأكيد هيبقى لوج 6. من خصائص اللوغاريتمات إن أنت تقدر تقول لوج 2 في 3 فبيساوي لوج 2 زائد لوج 3، كأنك حولت عملية الضرب إلى عملية أهو. يعني هتبقى لوج 2 للأساس 10 زائد لوج 3 للأساس 10 بيساوي لوج 6 للأساس 10. كل ما هنالك إن في مسطرة هتقيس بيها 2 أو لوج 2 يعني هتبقى متقسمة، والمسطرة التانية تحط عليها 3 ويبقى مجموع المسافتين، المسافة الأولى على المسطرة الأولانية والمسافة التانية على المسطرة التانية تديني 6. طب تعال نشوف الكلام ده. تعال نشوف. الأول هاخد 2. تمام. خلي المسطرة اللي فوق دي تتحرك، هي كانت المفروض واقفة هنا، تتحرك لغاية لما الواحد بتاعها يجي عند الاتنين بتاع المسطرة التانية. تمام. يبقى المسافة ده اهي من الواحد للاتنين ده اللي هو لوج 2. تمام. يبقى ناقص دلوقتي ايه؟ هجيب لوج 3 واجمع المسافتين هيديني لوج 6. خلاص ادي انا دلوقتي وقفت عند الاتنين. تمام. اجي عند المسطرة اللي فوق واخد مسافة اللي هي مقدارها 3 اللي هي لوج 3 اهي، امشي امشي 3. خلاص يبقى انا اخدت الاتنين اهو والتلاتة هنا، يبقى المسافة من هنا لهنا المفروض تكون 6 اللوج 6 اهو. يبقى انت كده تخيل انت مش عارف ضرب 2 في 3، فيبقى انت حطيت المسطرة دي عند الاتنين معايا، وبعد كده من عند الواحد بتاع المسطرة اللي فوق جبت التلاتة، وبص تحت عند المسطرة التانية دي شوف الخط بتاع الكيرسور واصل فين، لقيته عند 6. يبقى دلوقتي 2 في 3 يساوي 6. نفس الفكرة تقدر تعملها في عملية القسمة. فالقسمة هتبقى بالنسبة لي تبقى إيه؟ بخصائص اللوغاريتمات هتبقى طرح. معايا؟ نفس الفكرة أهو. 6 على 3 المفروض بتساوي 2، خد لوج الطرفين يبقى لوج 6 على 3 بيساوي لوج 2، وبخصائص اللوغاريتم يبقى لوج 6 ناقص لوج 3 يساوي لوج 2. فأنت هتعمل إيه؟ هتجيب لوج 6 كمسافة وتطرح منه لوج إيه؟ 3 كمسافة، هيطلع لي المفروض طلع لي المسافة الفرق بينهم يعني لوج 2. طب تعال نشوف الكلام ده. أهو أجي عند المسطرة الأولانية. تمام. وأعمل إيه؟ أهي أدي المسطرة الأولانية أهيت. خلاص. أجيب الستة، أدي المسافة الستة من هنا لهنا. تمام. خلاص. يبقى المسطرة الأولانية اللي هي تحت دي خدت منها قد إيه؟ 6 من هنا لهنا. وأجيب المسطرة التانية. خلاص. وأحط بدايتها من الناحية دي عند الستة، وأمشي بالعكس 3. يبقى دي قد إيه؟ لوج 3. يبقى أنت من هنا لهنا لوج 6، ومن هنا لهنا لوج 3. خلاص. يبقى الفرق دلوقتي المفروض يكون ايه؟ لوج 2. تعالى امشي مع الكيرسور كده اهو. خلاص هذا الحل بتاعك اللي هو 2. تمام. طبعا هو خلي بالك الموضوع ده محتاج تدريب وكده. تعالى نشوف فيديو بسيط كده عن السلايد رول ونشوف بعض الأمثلة.
The slide rule is one of the coolest and perhaps most important technological instruments that people today have only the dimmest idea what it is. Right around the time MIT moves from Boston to Cambridge, the archetypal instrument, bar none, for the engineer is the slide rule. This is what people, went to the moon on. You can see those famous scenes in the movie Apollo 13 where they're all whipping out their slide rules. Well, that isn't for show. That's what they use. So what happens? Why do they go out of fashion in the mid-70s? Well, not surprising, the digital calculator and computer has a big impact on this.
And for a simple number to begin with, we'll take 2 times 3, just to illustrate. You all know the answer, of course. But we'll take the simple example so that you can see how to use the rule. And if, when you've learned, you've forgotten after a few days, always start with simple numbers you know the answer to, and it will be easy to pick it up again. Now we're going to multiply 2 times 3, and that is equal to 6. Now what we do is start with this index 1 on the C-scale and put it opposite our first number, which is 2. So we put this index on the scale opposite 2. Now line it up exactly right there. The index on the C-scale opposite our first number. Then we follow along this C-scale until we come to our second number. And our second number is right there. 2 times 3 is equal to 6. Now usually one would put the slider here on the 3 and read below it the 6. But I'm using this pointer because it's a little easier for you to see. So 2 times 3 is 6. A little harder product. 25 times 3, which you all can see gives 75. 25 times 3, how would we do that? Our first number is 25. So we come up here to our D scale and let this represent 20 and this represent 30. And 25 was here. So we put our index C right on the 25. And then we multiply that by 3. So we go along the scale to 3 and come down and we find 75. This would be 70, 80, 75. All right, now let's take a little harder number. 2.4 times 35. Now on the slide rule, you forget the decimal point until you get your answer. So this is the same as multiplying 24 times 35. 2 significant figures times 2. 24 times 35. Now we come up to our rule, and here's 25. Here would be 24. So 24 is right here. Times 35 carries us over here. Here's 35 at this point, and right down here is 84. Now, in the answer, we don't know whether it's 84 or 8.4 or 840. So you write your number down here, and then you examine these figures, and you round them out to the even numbers. This is approximately 2, and this is approximately 30. 2 times 30 would be 60. That tells us the decimal point is here. 84 is not far from 60. The decimal point goes there. Certainly 2 times 30 is not going to give 6, nor is it going to give 600. 2 times 30 is 60. So it tells us the decimal point is there, not there, nor there. So you get the decimal point by inspection. Now let's take 2.6 times 5.5. 2.6 times 5.5. Now we go up to our scale, and we set this index on 2.6. And then we come along the scale, and we see we run off. We can't read our answer. So what do? We slip the stick back in the other direction. We come back to our 2 point. What did I have here? I set that on 2.7, didn't I, instead of 2.6. Well, anyway, we're off the scale. So we come back with our index here to 2.6 in the other direction. See if I get that right. 2.5, 2.6. 2.6 times 5.5. Now we go along the upper scale to our second number, and it comes right here, 5.5. So we come down here, and our answer is 1.4. And now here we have to guess how far it is between there if we want to interpolate. Our answer would be 1.43. See, 1.4 is to there, 1, 2, 3. 143, and we could say 2. But the three figures, it would be 143. So we write down 143. Decimal point, we examine these two numbers. You see, this is around 2 or 3, and this is around 5. Now 3 times 5, or 2 times 5, would be 10 or 15. It tells us the answer has the decimal point here. It couldn't be 1, 2 times 5, 43. So there's the decimal point. Now let's take a 3 significant figure number, like the one of the area of our rectangle. 345, you remember, by 234. 345 by 234. Now we slide this along. Here would be 340, and here would be 5. 345, we'd put our index right there. 301 to 4, and here's halfway between. 345 times 234. This would be 200, 10, 20, 30, and this would be 4 here. Now our answer is 8 here. I better put this slider out. 234 is right there. Now here's 8. There's 8, 1. So it's not quite up to 1. We'd have to interpolate here. 8, 0. This would be 8, 1. This would be 8, 0, 7 or 8. It looks merely 7. So our answer would be, and we could write it down here, 807. Now to find the decimal point, we round off the numbers. 200, roughly, times 300. 200 times 300 would give us 6, and then 4 zeros. So we see this should be 80,700. And you remember the answer we got was 807 something in here. These are not significant figures because this is only correct or nearly correct in the third significant figure. Now let's carry out division processes, see how they're done. Here again we use the lower scales. And to take a simple example, let's take 6 divided by 3 equals 2. You can all do it in your head. But let's try it on the slide rule. Now this is the reverse process of multiplication. What you do is set these two numbers up on your C and D scales upside down. The 6 on the D scale and 3 opposite on the C scale. So we'll find 6, the numerator, and that is here. And then we'll bring along opposite it, and then over on our index here, we find 2. Because you see 2 times 3 is 6. 6 divided by 3 is... Now let's take a little more complicated number. 28 divided by 4, which mentally you can see gives 7. 28 divided by 4. Now we go up on this D scale and find 28. That would be here. Here's 30. That would be 28 divided by 4. Bring along 4, opposite it, and then look to the index that is on the rule. And the answer is 7. Now if you'd gone the other direction to the other index, you'd find it off the rule. You couldn't read it. Now let's take a little more complicated number. 675 divided by 121. Both have 3 significant figures. 675 by 121. Always set the top one up on the bottom scale. 670 would be there. 675 would be there. Now I'll put the slider there. That's the way you'd normally do it. 675 would be there. And then your other number, 121, is brought directly over it. Now here is 100 and 200. 121, there's 120 there. 121 is right under the slider mark. And the answer is right here. And that will be 5, 5, and about 8, 7 or 8 in there. You have to interpolate. this is 5, this is 1, this is 5, 5, 5, 6, 5, 5, 7, or 8. And the answer actually is 5, 5, 8. Now you get the decimal point here by looking again at the numbers. This is roughly 600 divided by 100. 100 goes into 600 6 times. So that tells us the decimal point goes here. And the answer is really 5.58. Now here's a process using a little larger number, 9528 divided by 695. 9528 divided by 695 is 13.71. 9528. To do that, we'll go over the far right-hand side and pick up 95. There's 96. 9528 would be about here. I better put the slider over that position. And divided by 695. So we find 6. And here's 869. 695 is right under the mark. Now this index is off, so we have to go way over to the left and find the answer here as 137. 137. We can't get the fourth significant figure because the slide rule in general is only good to 3 significant figures. So we get as an answer 137, and the examination of the figures shows its decimal point is here. Now let's take square roots of some numbers. Suppose we start with the square root of 25, which you all know is 5. Now for this purpose, you put the scales and the sliding scale directly opposite each other. You don't have to do this, but you may make an error if you slide them even with each other and leave them there. Then what you do is take your number, find it on the upper scale. We'll go way over here to the left and examine this. Now, you don't know whether to go to the right-hand scale or the left, so we look first at some simple numbers we know. Here's a 4 and a 2. The square root of 4 is 2. You go over here to 9, it's 3. If you go along here, there's 15, this can be 16. The square root of 16 is 4. Now we wanted the square root of 25, so here's 20, 30, there's 25, and the square root of it is 5. Now suppose you don't know on the upper scales whether to come to the 4 here, or whether you go to the 4 on the other side. Now the rule is this: if the number's between 1 and 10, you use the left-hand upper scale. If it's between 10 and 100, you use the right-hand scale. Between 100 and 1,000, in the left-hand scale. And you can do that by examination. Now the square root of 400 says we should use this scale. And the square root of 4 is 20. So you take the square roots by finding your number on the top scale, and the square root of it will come out below. To square numbers, you just do the reverse process. You can either find your number here and read it off on the upper scale, which gives you the square, like square of 2 is 4 and the square of 3 is 9. Or you can multiply 3 times 3 or 4 times 4, whatever your number is, by using just the C and D scales alone, using the regular multiplication process. Now a little practice with the slide rule should enable you to carry out these simple operations: multiplication, division, square root, and squares. Lots of practice will save you a great deal of time. So get yourself a slide rule. You can all afford one. The cheapest ones are perfectly good and will give you 3 significant figures. Examine them carefully when you go to the store to buy one. Line the scales up at the left and see that they agree with each other all along, that one of them hasn't shrunk a little. So get yourself a slide rule. Learn how to use it. It will save you a lot of time and energy.
سنة 1623 قامت شيكارد بناء على اللي اتعلمه يعني من نيبير اللي انتوا شفتوها، اللي هو النيبير بونز. قدر ان هو يعمل الآلة اللي انتوا شايفينها ديت، وسموها تشيكارد كالكوليتنج كلوك. وقدرت الآلة دي، طبعا هي مكونة من تروس من جوه، وهنشوف دلوقتي في الفيديو تكوينها عامل ازاي. هتلاقي تكوينها فعلا بسيط، وفكرتها مبنية على النيبير بونز. معايا؟ فاكرين طبعا النيبير بونز ده احنا قلناه في أول الفيديو. والآلة دي كان عندها القدرة إنها تقوم بعملية الضرب وعملية القسم. طبعا في النيبير بونز كان بتستخدم انت الستيكس او البارز او البونز بتاعت نيبير، وكنت بتستخدم معاك ورق كده في جنب عشان تقوم بعملية الايه الجمع. طبعا هو كان حول عملية الضرب إلى عملية جمع، وكنت محتاج ورقة، خصوصا لما انت تكون بتضرب مثلا 3 أرقام 3 خانات، يعني في 3 خانات، فكنت محتاج إن أنت يكون معاك ورقة وتسجل فيها الايه الناتج اللي بيطلع، أو بتقوم بالعملية كلها عن طريق الايه الورقة دي يعني والنبر. هنا في المكنة اللي عملها تشيكر، طبعا زي ما انتم شايفين كلها من الخشب. معايا؟ قدر ان هو يستغنى عن موضوع الورق، وكل الكلام بيكون متسجل. آه، دي لو انتوا بصيتوا فعلا المنطقة ديت هي النيبير بونز، وهنا شوية تروس هتشوف الوضع ماشي فيها ازاي، ويقدر هو يطلع الناتج فعلا من هنا. بس طبعا هو بياخد شوية خطوات معايا، بس بدل ما يكتب الخطوات ديت بيكتبها على ورق، بيقدر يستغل الماشين ديت إنها تعمل الكلام ده بدون الحاجة إلى ورق. هنا كاتبين إن الآلة دي ما خدتش يعني الشهرة الكاملة، بسبب إن اللي هو الراجل تشيكر ده مات في طاعون والكلام ده. وتعالى نشوف فيديو هيوضح لك التركيب بتاعها من جوه ازاي المكنة ديت معايا. وهشوف بقى مثال على عملية الضرب وعملية القسمة. طبعا زي ما انتم شايفين موضوع التروس اللي هو بخشب هتخلي ان شوية الدقة بتاعة الانسترومنت ديت او الماشين دي لو صح التعبير هتبقى شوية فيها كلام.
In this video I would like to show multiplication with the Scheckt calculator from 1623, as well multiplication with Napier's bones, that are calculating bars that were invented a few years before Schickard by the Scottish scholar John Napier and published in 1617. 6 years later William Schickard took those bones or bars and mounted them on turnable cylinders, creating this multiplier unit. If we take a look at the 3 and at 1 and open shift register number 7, we'll see 3 multiplied by 7 is 2 in the tens column and 1 in the ones column. The same in the machine and on the Napier's bones. So let us multiply 31 by 7. We have here the 7 in the ones column. I'm transferring that into the adder unit. we have 1 in the tens column and 2 in the hundreds column. So the result is 217. And how multiplication works with multipliers that are longer than 1 digit, we'll show that later in the video.
Before I show multiplication with the Schickard machine, I would like to show what Scottish scholar John Napier invented a few years before Schickard to support manual multiplication. Napier invented calculating rods called Napier's bones and published them in 1617, just 6 years before Schickard constructed his machine. There are 10 different rods for the numbers from 0 to 9, and additionally a rod vertically labeled with the digits from 1 to 9. This additional rod acts as the multiplier. The other 10 rods display multiplication tables for each number multiplied by 1 to 9. I demonstrate that using rod number 6 with the multiplier rod beside it. Now I want to multiply 6 by 7. Here you can see that the result is 42. One could also say that it is 2 plus 40, or 2 in the ones column and 4 in the tens column. If you want to multiply a 2-digit number, for example 76, then the principle is the same. We take the rods labeled 7 and 6 and the multiplier rod beside them. Then we multiply 76 by 7. We have a 2 in the ones column and a 4 and a 9 in the tens column and a 4 in the hundreds column. Calculated from behind, this is 2, 4 plus 9, which is 13, or 3 in the tens column and a tens carry into the hundreds column, plus 400. The result is 532. This works with larger numbers in the same way. Now let's multiply 1276 by 7. We take the required rods 1, 2, 7, 6 and the multiplier rod. The result read from behind is 2, 3, 9, 8. So the result is 8932. This works really good as long as the multiplier is a single-digit number. But when the multiplier is larger than 1 digit, multiplication with Napier's bones becomes equid or awkward. For larger multipliers we need paper to write down the intermediate results and calculate the final result. Now I want to show the multiplication of 1276 and 237. We start with the ones column of the multiplier. In the first step we multiply 1276 by 7. This is a 2, 3, 9, 8 read from behind. I note that on a piece of paper, 8932. In the second step we multiply by 30, or 3 in the tens column. I note the result shifted by 1 in the tens column. 1276 multiplied by 3 is 8283, read from behind. That is 3828 in the tens column. And finally we multiply by 2 in the hundreds column. The result of that is 2552. I note 2552 in the hundreds column, then I sum up the intermediate results. 2, 1, there we have a carrying, 4, again a carrying, 9, 17, 22, 2 with a carrying of 2, 5 plus 5, 0 plus a carrying, 3. The final result is 302,412. But as we saw, we needed paper for the multiplication of larger numbers using Napier's bones. The great advantage of the Schickard machine is that we can perform the same multiplication supported by a machine and without any paper. So maybe we can say that Schickard invented the paperless office. I would like to show multiplication with the Schickard machine now. I'm entering the first number, 1276, in the top row of the multiplier. 1, 2, 7, 6. And the second number in the buffer memory, 237, 2, 3, 7, 7. Then I'm going through the decimal positions of the second number from right to left. In the ones column there's a 7, therefore I open register number 7. In the ones column there's a 2. In the tens column 4, the 9, and here 4, again 4, then 1, 7. That already was a multiplication by 7. Now we are coming to the tens column of the multiplier, 30. I'm opening register number 3. So now we are in the tens column, 8. Okay, here I had to help a little bit. Was it carrying over 2 positions? Now 1, again 1, then 2, 6, finally 3. That was the multiplication by 30. Now we are coming to the hundreds column, so multiplication by 200. I'm opening register number 2. Here we have a 2, then 1 and 4, again 1, 4, and finally 2. That was a complete multiplication. The result is now visible in the adder. 302,412. I want to show that a little bit closer. I zoom in. 302,412. We have seen that the multiplication with the Schickard machine is easier than with Napier's bones and completely without using paper. That was all that I wanted to show.
In this video I would like to show division with the Scheckt calculator from 1623. I've shown the other basic arithmetic operations in other videos, so let's see how division can be performed with this machine. Division can be seen as the opposite of multiplication, and this is directly the way how it is performed or computed with this machine. First I want to show a very simple example, the division of 2 small integer numbers, to show the principle of division. And as well I want to show that floating point division was possible with this nearly 400 years old machine as well. I want to show division of 75 divided by pi. So let's start with the easy example. I want to divide 581 by 7. I'm entering 581 in the adder and 7 in the multiplier. So we want to divide 581 by 7. So we have first we have to choose the first position of the result, and I'm opening all windows of the multiplier, and then we have to find the maximum number that we can subtract from the number in the adder. The number in the adder is 581 or 58. So let's see what's the maximum number. We have a 7, 14, 21, 28, 35, 42, 49, 56, 63. So 63 would be too large. 42, 49, 56. 56 is the right number. 56 is the maximum number that we can subtract. It is in the 8th column, or in the 8th row. So 8 is the first position of the result. So I'm entering 8 in the buffer, the first position of the result, and then I have to subtract 56. 56. So now 21 is left in the adder, and for the second position of the result we are doing just the same thing. We have a 7 in the first row, 14 in the second row, and 21 in the third row. So 21 is exactly the number that we were choosing. So 3 is the second position of the result. I'm entering 3 in the buffer, and then I subtract 21. So all numbers or all digits in the adder are 0 now, and that does mean that we are finished. So we've found the result. The result is 83. 581 divided by 7 is 83. That was a simple example.
So let us do a floating point division now. I want to divide 75 by pi. I'm entering 75 in the leftward position in the adder, and pi in the top row of the multiplier. 3, 1, 4, 1, 5, 9. Pi with 6 digits precision. Now again I'm searching for the maximum number sequence that is less or equal 75. We have 60 in the second row, 90 or 9 in the third row, that's less than 60. In the sixth row, 18, 21, 24, 27. So the second row has 1. 2 is the first digit of the result. Subtracting 6, 2, 8, 2, 1, again 1, and 8 in the last column. So we have to find the second digit of the result. We are searching for a number less than 121. 60, 90, 124, that is too much. So 90 from the third row is better than that. 15, 18, 21, 24, 27. So the third row has 1. 3 is the second digit of the result. I'm subtracting 9. So let's guess what the result will be. 75 divided by 3 would be 25, and 75 divided by pi must be a little bit less. So the result will be 23 with some digits behind the point. So we are searching now for the first position after the point, 23 point, and again we are searching the maximum number sequence less or equal 27. We have 18, 21 is more than 18, 24 is more than 21, and 279 is too much, so 248 is better as the best. So first position after the point is 8, and we have to subtract 2, 4, 8, oh, had to correct that, 3, 8, so we have found the first position after the point. The result by now is 23.8. So we have to find the second position after the point now. Again, the maximum number sequence less or equal 2303. 31 or 3, 6, 9, 12, 15, 18, 21, 24, that is too much, 27 is too much as well, so the second position after the point is 7, and we have to subtract 2, 1, 7, 2, and 8. So the result by now is 23.87. Now we are searching for the third position after the point. And again, the maximum number sequence less or equal 105. 90. 18, 21, 24, 27, so the third row has won, 90. Subtract 9. 3 and 1. So there are only 11 left in the adder, and we have to find the last position of the result, the last digit of the result, fourth position behind the point. And the third row was 9, 2. So the third row has 1 again. Can subtract 9. So there are 2 left in the adder, but we have found 6 digits of the result. And that is the maximum precision. So we are finished. 75 divided by pi is 23.8733. Finished.
كده قدرنا نتعرف على جزء من تاريخ الكمبيوتر، واللي هو بدأ من الناس اللي هم كانوا هم الكمبيوترز، وبعدين الاباكوس والنيبير بونز، وبعد كده اتكلمنا عن السلايد رول والتشيكرد كالكوليتنج كلوك. يعني احنا هنستكفى المحاضرة ديت لغاية هنا كجزء أول، وإن شاء الله نكمل تاريخ الكمبيوتر، أو يعني بريف كده عن تاريخ الكمبيوتر في الجزء الثاني من المحاضرة. شكرا جزيلا.